Okay, this video was prepared for MAE 3323 Tulsa section on October 14th, 2011 to be the replacement lecture because we are missing class this week because of fall break. First thing I want to do is open up the notes, and so you have access to the notes. They're on the D2L site. And for the benefit of for the benefit of half the class who left early after the test and missed the discussion where I really defined strain energy and the rules for Castigliano, I'm going to do a very, very brief update, but I'm going to leave it up to you folks who left class to go ahead and study the notes more carefully, study the book more carefully, to try to catch up for yourself on what I talked about, but I'll at least point out what you need to read. What you need to read is the idea that structures store energy just like springs store energy, because the spring is a structure. And if we can calculate the energy in a spring and use it to do other calculations, we can also calculate the energy in the structure and use it to do other calculations. And so this section talks about things like deflections because of an axial tension member and calculating the energy as the average force F over 2 times the total deflection, and then for axial tension compression, filling in these two values will give us the total energy stored in an axial tension member. By the same argument, we could say that the total energy stored in a torsional member, presumably a round circular rod, would come from here. Direct shear we talked about briefly as being incredibly hard to produce. But this would be the energy stored because of direct shear. Skipping all of this kind of stuff, but basically if we have a beam in bending, okay, the energy stored at a location in a beam in bending, m squared over 2EI, we talked about it briefly, but I'll let you read that. The VQ over IB type shear energy for a beam, formula given here, but there's a C correction factor depending on the shape of the beam. And then we have an example that says find the strain energy due to shear in a rectangular cross-section beam simply supported and having a uniformly distributed load. Now if we're talking about shear in a beam, what we're talking about is the VQ over IB type shear. Jumping back here, notice we're going to need V, but V is going to vary with X. This is an integral. X is our independent variable. V, the shear, will vary with X within the beam. Okay, and if we look at simply supported beam, uniformly distributed load, okay, the shear at any point in the beam will come from, and they say just go look it up in table A97. But you could draw the shear diagram for this thing, and you would see that there would be a shear piece from the reaction at left hand end, right here, and then a shear piece from the distributed load at any point called X. Since it's a rectangular cross-section beam, looking back at the table, we'll see that we use a C equal 1.2, and using our energy equation for transverse shear in a beam, CV squared dx over 2AG. The 2AG is a constant, doesn't depend on X. 1.2 doesn't depend on X. We take the V squared quantity, we square it, we integrate it, and we come up with this. That would be the energy in a beam due to transverse shear. Next one would be a cantilever has a concentrated load F. So we have a load F at the end, and we want to calculate all of the energy stored in this beam simply because of bending. Okay, notice where X is defined on this one, X heading to the right. Okay, and the moment in this one is going to be minus F times X. What we're doing is we're measuring X from the left into the beam, and at any point in the beam the moment there is minus F times X. Going back to the energy equation for bending, integral of m of x squared dx over 2EI. The EI will be constants. We can bring that outside. We'll be integrating m squared dx over the entire length of the beam. The moment, again, was minus fx, so the moment squared, fx squared. 2EI could be brought outside. Integrating that gives us an f squared L cubed over 6EI. That's the energy in the beam. Okay, so energy in structures exists and can be calculated. This, for those of you who missed class, read this sentence about 7 times. I'm going to read it for you once, but I'm going to modify it just a little bit, so I'll pause when I modify it just a little bit. Castigliano's theorem states that when forces act on a structure subject to small displacements, not large displacements, when that happens, we can calculate the displacement that corresponds to the force. Correspondence means we can calculate the displacement at the place where the force is applied and in the direction of the force. And when we calculate that displacement, we'll find that it is equal to the partial derivative of the total strain energy that we computed just earlier for a few structures, the partial derivative of that strain energy with respect to the force itself. Okay, again, so if we apply a force to a structure and we write the strain energy for the structure in terms of that force, if we take that strain energy equation and take the partial derivative of that strain energy equation with respect to the force itself, that will give us the deflection of that structure at the place where the force is applied in the direction that the force is applied. Not anywhere else and not in any other direction. This is a brief summary. It says the deflection of the place where force is applied is the partial derivative of the strain energy with respect to that force. If the force variable is actually a moment variable, which is a rotational effort, then we have a similar idea, well, the same idea, that says if we take the partial of the energy with respect to an applied moment, we're not going to get a deflection, we're going to get a slope. And we'll use that in some example problems. Okay, let's see. This one simply says, look, let's go back and get the energy that we found for axial tension earlier, and that was F squared L over 2AE. What happens if we take the partial derivative of that axial tension energy with respect to the load F? Okay, taking partial derivatives means we hold everything else constant while we take the derivative with respect to F. And that gives us an FL over AE quantity, and that certainly is the deflection equation for an axial tension member under a direct load F. And then the other would be if we go look up the torsional energy in a circular beam. And we take the partial derivative of that torsional energy with respect to the torque, which is a rotational kind of thing. Then that partial derivative gives us TL over GJ, which we've already seen in this class is the slope, or the change in angle measured in radians of a beam in torsion. Excuse me. Now, I said look at this carefully. So, Castigliano is somewhat limiting in that we can only calculate deflections where we have loads, nowhere else. And we can only calculate deflections in the direction of that applied load. What if we want to know the deflection somewhere else, or we want to know the deflection at a point where we have a load, but we want to know the deflection in another direction? Well, we do have a very nice option. Okay, and so those of you who missed class again, read this about 7 times. Okay, but it says what we can do is we can apply a fake load to a structure anywhere we want, can't we? I mean, it's our option to apply other loads to any structure we have. When we do that, we're going to call it a fictitious load. It's not really there, but we're going to pretend we have a load there. We're going to typically name that load Q, and we will then find the deflection of the structure, and I need to pause because my phone's ringing. Okay, well, I just answered my phone, and I forgot exactly what my train of thought other was. We can place that load Q anywhere we want, and then we can take, for the structure, we can find the deflection at the place where we applied Q, in the direction that we applied Q. And that deflection will be calculated in terms of the magnitude of Q. But we can use any magnitude for Q that we want, but there's a very special one, the deflection magnitude value for Q, that makes it disappear. We can set Q equal to 0 after we've solved the deflection problem if we want to. That's what all of this stuff says. It says we can calculate the deflection at the location where we choose to place the dummy load, in the direction that we place the dummy load, and that deflection in the direction of Q at the location of Q is partial of U with respect to Q. But if we then set Q equal to 0, that's the special thing, then what we end up with is that is the deflection at that special place in the direction of the special place because of all the other loads while we set Q equal to 0. Okay. Now, I believe the way my notes were arranged that this next example does not implement that idea. We're going to be seeing so many other examples. You look at this one on your own. Okay. Now, this is another paragraph to read 7 times. Going back to the principle of using dummy loads to calculate deflections where there is no real load. There's going to be some tactics in the problem. There's going to be a lot of work to do, as you will see later. One of the things we can do to save a lot of time is strategically set Q equal to 0 as early as possible. Now, the basic jobs that we're going to have to do is write moment of x equations or torsion of x equations in terms of all the loads, possibly including dummy loads, and then we're going to have to put those into energy equations, and then from the energy equations we can calculate deflections, and at that point we could set Q equal to 0 if we have dummy loads. It turns out we can set Q equal to 0 earlier than that. We don't have to wait to the very end as implied by this statement right here, which says set Q equal to 0 at the end. We can actually set it equal to 0 earlier than that, and when we do, there is some time savings. Okay, and we also, the other thing that we can do is we can take our partial derivatives earlier than is implied by this equation. We don't have to calculate the energy using the integrals typically and then take our partial derivatives. We actually can take our partial derivative before we do the calculations on the integrals. So set Q equal to 0 early, which will be actually before we do the integrations, and take the partial derivatives of the energy equation early before we do the integration. That's what is what's being said right here has nothing to do with Q. What's being said right here is, yes, it's true that the deflection of a structure is equal to the partial of its energy with respect to the load. But if you look back at the energy equation, and let's look particularly for bending, recall that the energy equation was the integral of m squared over 2EI. And I guess I will just jump back to that and remind you. For bending, integral m squared over 2EI. Now, what if we go ahead and take the partial of this thing inside the integral with respect to f right now, and realize that 2EI doesn't depend on the load f. Let's move it outside. What is the partial of m squared? And m does depend on f. What's the partial of m squared with respect to f? It's going to be 2m times the partial of m with respect to f, because m is squared. So we first say the partial of m squared is 2m, then the partial of m with respect to f. See how that plays out in this equation back here. And that's precisely what this says. Let's see. Okay, for bending, the 2m, but the 2 canceled the 2 that existed in the denominator earlier. What we're left with is m times the partial of m with respect to f. We can take the partial derivative before we integrate. That will save time. Then the other one relating to q is, as soon as we've taken the partial derivative, anywhere q appears in here, if we're using a dummy load, we can now set q equal to 0 after we've done the partial derivatives, not before. Okay, and so we will see examples of that. Take a look at this one, work that one yourself. Let's talk about this one. This is an interesting problem. We'll talk about it for a moment, and then we're going to jump to some special problems that I've prepared. So we have a structure, and our question is, let's see, the problem statement's not showing up. but I'm pretty sure we're going to want to calculate the deflection at point B in the direction of point B. We have a load there so that we can in fact calculate the deflection at B in the direction of F. And we have to write the energy terms for this interesting structure, and we've got to capture all the energy. Now I claim that we're going to have some energy due to VQ over IB shear. It's probably going to be small. I would be inclined to ignore it. But we're going to have some energy due to bending, clearly. And we're going to have some energy due to torsion, clearly. And we're going to have to write all of those energy terms in terms of some variable that locates us within the structure, and then we're going to have to integrate all that stuff. All right, so calculating the deflection at B is the partial of the energy with respect to F. Now, they've done this a little differently than I would do it, in that they actually calculated a piece of the deflection happening because of what's happening only in BC. That's not the whole deflection, it's only a piece of the deflection at B. And if we look at what's happening between B and C, the reason we're going to deflect toward our right is because of bending. Okay, and so deflection in the BC range only is our 1 over EI, our moment equation, times the partial of the moment with respect to F. They're leaving a bit out here, but but moment anywhere measuring in the Y direction. So let's say Y is where my mouse is. My moment is F times Y. Moment is F times Y. You know what? The minus sign is not real important because it's going to cancel out. Now, what is the partial of Fy with respect to F? It's the minus Y term. So this is M. This is partial of M with respect to F. Written in terms of Y instead of X. That's fine. Integrating dy. And we get a tiny piece of deflection because of F and this short section, Fa cubed over 3EI. That'll be deflection in the direction of load F. But we're also going to get some deflection of B because of this structure here between C and D. The structure CD is going to bend outward, but it's also going to twist and torque outward. Both of those together give us deflection. Let's calculate the deflection at B because of the torsional energy at CD. So that deflection would be the partial of energy, torsional energy with respect to F. Okay, and that would be the torque times the partial of torque with respect to load F over GJ. We saw that energy term earlier, and this one doesn't need an integral. It could be written as an integral. Okay, and plugging in the torque, which is constant, F times A, times the partial of the torque with respect to F, that'd just be an A term. And let's see, the length of this section was called B, dividing by GJ. Here's another piece of deflection at B. In the end, we'll be adding all these pieces up to get the total deflection at point B. Now, there's another piece of deflection at B because of what's happening in this range. That's because of the beam bending in this range. So we're going to have to write the moment in this range because of F. If we measure a quantity x equals 0 here, moving to the right, then my moment for bending is just going to be F times x. And so my deflection due to bending is going to be 1 over EI, the integral of M, which is minus Fx, times the partial of M with respect to F, which is minus x. Notice the minus signs cancel. If we had left the minus signs off, there'd still be no minus sign. So the minus signs really don't matter that much. But integrating this thing, we get a piece, Fb cubed over 3EI, which is the deflection at B because of the bending in this piece. Now we're going to get a deflection at B in the direction of F because of bending downward of this section. Bending downward of this section will cause this to move to the right. And if we were including axial tension, we could also get some deflection out of this because of axial tension. I don't remember if it was included or not, but this is our region D to G. Let's see what we have here. Okay, yes, we are going to get the deflection because of axial tension, and the energy due to axial tension was F squared L over AE, but the partial of F squared with respect to the load F is F times the partial of the generic loading with respect to the specific load. Applying that, this is the axial deformation of this one, which will contribute to the deflection at B. And then we have a bending where we're going to have to write the bending moment, and we'll look at that in just a second. We'll have to write the bending equation, and then we'll integrate the energy terms. Okay, the moment in this section, because of this load F, is actually a constant, and it is a constant moment F times A. And so, let's see. Actually, sorry, there are two pieces of bending. There's a bending outward because, there's a bending outward, and then there's also a bending down. And presumably, are we going to deal with both of those bendings? Okay, we're going to have an F times B. We have a bending outward energy, and that moment is F times B. And so our 1 over EI integral of the moment, FB, times the partial of the moment with respect to F, that just leaves the B, integrating, here's the other one. I knew there had to be two pieces of moment. Then there is a moment that we'll call this beam to bend downward. That moment is a constant FA. And so here is our FA moment. Then the partial of FA with respect to F is just A. Integrating these two pieces gives the final piece of deflection, again, at B in this direction to the right, because that's the direction the load was applied. Putting all those energy pieces together means we just add up everything we've done so far, maybe do a little bit of simplification, and this is the deflection at point B in the direction of the load F because of load F. Kind of a messy problem, and we'll see some more of those. Okay, I said on this one, now get the downward deflection. If I don't have that one already solved and talk about it, well, let's just talk about how we would do it. And this would be a very good one for you to try. If I want to know how much B moves down, I don't have a load in the downward direction, but I can invent one, and I can place a dummy load Q acting right there. And now I do all of my energy terms through the entire structure, considering both F and Q. If I ignore F, I'm not going to get any deflections at all when I set Q equal to 0. Okay, I need to pay attention to what's happening with both F and Q, and I'm going to get some additional terms, write all of my energy terms, take those partials, and then set Q equal to 0 and calculate. We're going to look at some easier versions of that kind of problem first. Curved members, I will come back to curved members just a little bit later, or maybe I'll talk about curved members next time we meet. I'll decide that in just a little while. Now what I want to do is transition to a, let's see, no, actually I want to jump ahead to another idea, okay, called statically indeterminate problems. And just like we used the trick of a dummy load Q to be able to calculate deflections at places that don't have loads, we're also going to use another trick with Castigliano to solve statically indeterminate problems. Now, what do we mean by statically indeterminate problems? We're talking about structures where there are reactions within the structure that cannot be calculated with just the equations of statics, probably because we have too many reactions. And so this should be an example right here. What we have is a cantilevered beam, but we've messed up that beautifully statically determinate cantilevered beam by placing an end support on it. That structure is indeterminate. We cannot calculate the reaction at point B without understanding how this beam itself behaves, including its moment of inertia, Young's modulus, those kinds of things. And if we look at a static diagram of this thing, we know that this cantilevered wall gives us a vertical shear and a moment. And what we have on this thing is 3 reactions that we could solve, but we've only really got 2 equations to solve. Sum of forces in the vertical direction equals 0, and sum of moments about a point equals 0. With 2 equations, we can't solve for these 3 unknowns, but we are going to apply a Castigliano trick. And here's the trick. Okay, the trick, and then the words up ahead will say what, or up here will say what to do. But here's the trick. We don't have to apply a support there if we don't want to. We could change the structure, and we could instead apply a force there. Now, this support does indeed supply a force, right? That's its whole purpose. But it's a force that has a higher purpose, which is to cause the deflection at this point to always remain 0. So there is a force here that's always just enough to cause this deflection to remain 0. So what we can do is place a force, get rid of the support, place a force here, calculate the deflection at the end of a cantilevered beam without the support because of the force here and because of any other forces acting on it. But we'll be taking our partials with respect to this force that we place right here. And it's not a dummy load Q that we set equal to 0, because this support does apply a real force. We just don't know what it is. Okay, and it has a higher purpose to control deflection. What we'll do is we'll solve for the deflection equation here because of this load F, and then what we can do is set the deflection equation equal to 0 and solve for that unknown load F. We will have solved for the statically indeterminate reaction in terms of the applied load and geometry of the beam. Once we know this reaction, then we can use statics to solve for the other 2. Let's go look at what this thing says. It says, choose a redundant reaction. There may be alternatives. For this problem, I would probably choose the support and leave the cantilever alone. I choose that one, and I then write the equations of static equilibrium for the remaining reactions in terms of the applied load, or in terms of this load. That means if I pretend I know this one, I can do the statics on these and calculate these loads in terms of that load if necessary. It's not always necessary. Write the deflection equations for the location at the redundant reaction. Okay, set that equation equal to 0 and solve for the reaction. This will be very nice to see in an example problem, and so we're about to turn to some example problems. I'm going to pause right now and I'll be back in just a moment, and I've got a MathCAD document for you to look at.